All right, thanks, guys. We're about to start our final session. So we're continuing with our punch connections. And our first speaker is going to be Bea Gaillard-Lacour, who is going to tell us about a different regime entirely and what we could do with punch. All right, so go ahead and take it away.
Hey.
Let me double check that I actually unmuted. Unmuted that. All right, take two.
Perfect. Hey. Thank you so much, everyone, for sticking to almost the last session. I want to start by thanking the organizers for inviting me to give this talk. And I want to thank everyone because this community is incredibly welcoming. I'm a heliophysicist, but as you can see from the title, I'm a magnetosphere aeronomy person. So this might feel a bit of a disconnect, but this is an invitation because during the last 2 days, we have been talking about connections with punch, and I'm going to talk today about that high altitude aurora and how maybe the magnetosphere aeronomy community can help today. So yesterday, there were a couple of questions about the aurora and what do we talk about when we talk about the aurora. And this is very basic, but it's very important that we understand the very basic concepts. So when we talk about the aurora, we are talking about electrons and protons that precipitate into Earth's atmosphere. And they interact with neutrals in the atmosphere. Because of the densities in the atmosphere, as we know, it's going to be decreasing as we increase altitude. Usually the altitudes where we think about the aurora is about 100 kilometers. And this is different for what we are seeing for the high altitude aurora. You might know this better than I do, but let me tell you that as an auroral scientist, the high altitude aurora to me is very mysterious. So the observations of the high altitude aurora has been made with the SME instrument on board of Coriolis. And this is a white light imager. And what you are seeing here in the image, not sure if I can point, but you can see there with the arrow, I'm pointing at the aurora observed by the instrument. This is very high altitude because this is above.
Sorry, if you go like this, we can use the arrow.
Perfect, thank you. So there. This is very high altitude. This is above 800 kilometer altitude. So as you can think, the immediate question that we have is, if there are electrons and protons precipitating in that region, what are they colliding with, where the densities are so low? And the paper offers some suggestion, but I'm not completely sure whether or not we have demonstrated that. The other thing that the paper offers is the region where these observations occur. They say that they occur in the auroral oval, or what we call the polar cap. Differentiating those two is extremely important because the topology of the magnetic field in the two regions is different. So the dynamic, as you can imagine, is going to be different. What else? Unsurprisingly, the high altitude aurora is correlated with high geomagnetic activity, and the paper does offer a possibility for this. And they propose that this high altitude aurora is produced by the presence of N2+, produced by the high altitude ion outflow. To my knowledge, this might be the very first time that we are actually observing that outflow. So understanding whether or not those are the particles interacting with the electrons and ions is going to be extremely, extremely important. As you all know, PUNCH will be observing that high altitude aurora that I think many of us are looking to observe. So today, I'm planning to show you what the magnetospheric and the aeronomy community has, not only in situ, but also for remote sensing the aurora, that we could combine with the punch measurements that could help us understand what is the physics taking place at the 800 kilometer altitude. I don't need to tell you that for centuries, on Earth, we have been observing the aurora, and the community for the last few decades have been studying the aurora in situ with satellites and also from Earth with different instruments, optical and not optical. I'm going to be heavily explaining some of the optical instruments, but I'm also going to mention some of the non-optical instruments that we can use. I want to say thank you to my colleague, Vincent Ledvina, who took these images from Alaska. Some of us just interact with the cold and the snow by removing the snow that we get in the winter. He also gets this in his backyard, so who knows? So in terms of what we have, the Heliosystem Observatory provides us a very good suite of instruments and satellite emissions that will help us understand that is helping us understand the aurora. For example, we have the MMS mission in the magnetotail. We have the 5 Themis/Artemis satellites, and those satellites have been fundamental to understand the dynamic not only in the magnetotail, but also understand how the structures that we observe in the tail are producing some of the aurora that we are observing in the ionosphere. On top of that, a couple of days after PUNCH launches, we have EASY. And EASY is going to be observing or analyzing the currents in what we call the electrojet, the auroral electrojet. And a combination between PUNCH and EASY, it's extremely relevant too. Yesterday, we also heard about the possibilities for connections with the tracer missions. And we can keep adding and adding and adding. We have been using the HSO to study the aurora extremely well. Beside the HSO, we also have a system of satellite that has a similar orbit as PUNCH, and we have used it extensively to understand the aurora, and that is the Defense Meteorological Satellite Program, or DMSP. So DMSP has instruments that allow us to understand what is the energy of those precipitating electrons and ions. It has a dawn-dusk orbit very similar to PUNCH. So a combination between these two satellites is going to be extremely important. What you're seeing here in the image is actually an auroral observation from Svalbard, very north. And this is the precipitating electron fluxes that you can see here. These combinations of data is something that we do all the time. In addition, since DMSP has been operating for so long, the colleagues at APL have produced what is called the boundaries. So right now, the data has the boundaries, so we can know whether or not we are within the auroral oval, within the polar cap, or in a different region. So for understanding where this high altitude aurora is, DMSP is going to be extremely, extremely useful. Satellites have been game-changing when it comes to understanding the magnetosphere and the aeronomy system. And ground-based have done their part too. We have an extremely good coverage of ground-based observations, especially in the Northern Hemisphere. What you are seeing here in the figure up here is actually the ground-based part of those 5 Themis satellites. This is the Themis all-sky imagers. These are 21 cameras that are all over Canada and Alaska, and takes image of the aurora in white light every night. The coverage is spectacular. What you have here is north is going to be to the top. So this line indicates latitude increasing up, and then the circles here indicates longitude. This is just white light, so we cannot necessarily extract information such as energy and other things, but we have other instruments that we can use for that. So on top of this, you are seeing this very narrow plot. Those are meridian scanning photometers. So those do not allow us for that global imaging that the Themis ASI give us, but it gives us information in the different wavelengths that can be then converted into energy. And then we usually plot them latitude as a function of time, so we can get the dynamic of the aurora. With the improvement of commercial cameras, the field has also been partnering with what is called citizen scientists. And the type of data that they can capture is extremely amazing. So this is not a scientific instrument. This is actually a project called Aurora Eye. And this is a citizen scientist produce and deploy instrument, and they have several operating in North America. And right now people are talking to them to see, because this is a lower cost instrument, right? To take them and maybe deploy them to places where we do not have observations currently. So we are working with them, for example, when we're talking about rocket campaigns. Can we put one of these low-cost instruments somewhere in the field? So this also gives us the opportunity to sample areas where our high-resolution instruments might not be available. So this is going to give us maybe a smaller field of view with lower temporal resolution than our scientific instruments, but still very valuable data. When it comes to that high resolution data, we have many instruments. This is one example of an array that has a different type of instruments. So the one that you are seeing here, so this is a Transition Region Explorer from the University of Calgary. This is 7 cameras that are observing the aurora from the ground, and they measure in true RGB color. The cameras usually operate with 3-second time resolution, with the possibility of a campaign mode where they take 3 hertz time resolution data, so extremely detailed data. And these 2 cameras are actually showing you 2 examples of that. These examples are from Emma's PUNCH6 from the University of Calgary. Apart from the true color RGB data, to obtain the energy that we need, the cameras can be entered into an auroral transport code that allow us to get that energy information that we need. This array also has the near-infrared all-sky imagers, blue light imagers in the 7 sites, and even more importantly, 3 imaging spectrograph. So we can get the full spectrum of the aurora that is observed over this instrument. So this is an example of North America, and in the night side. But that is not everything that we have available for us right now. This is another example where imaging in Svalbard is also possible. The institute there also has 2 all-sky imagers and other instruments. And because of the latitude, because of the very high latitude, they actually capture the dayside aurora, and very often they observe structures within the polar cap. So if that high altitude aurora is produced within the polar cap, we should be able to capture it. And some of the instruments in North America should be able to capture it too. So for non-optical instruments, we also have many, many instruments. This is one example of one of my favorite instruments because it's extremely powerful. This is an incoherent scatter radar. And they usually measure electron and ion density, temperature, and plasma velocities. The distribution, the spatial distribution of the ISRs is relatively limited. However, what we can obtain, the information of the plasma dynamic that we can obtain with them is not only 2D, we can also get some of the 3D velocities for that plasma. So that will be very interesting when we think about a high altitude aurora to measure that outflow. So as a very, very quick summary, we have many instruments in the magnetosphere aeronomy community that can be used in connection with PUNCH. This is a list of some of them. We have 21 Themis all-sky imagers. We have red line imagers that are usually very useful to observe those very low energy precipitation, so dimmer aurora. We have the Transition Region Explorer in many different wavelengths, plus the 3 spectrograph. We have 2 all-sky imagers in Svalbard. We also have spectrograph data in Svalbard. And then we have, for sure, the 3 incoherent scatter radars, 1 in Alaska and 2 in northern Canada. On top of that, we also have an excellent coverage of ground-based magnetometers, GNSS receiver, coherent scatter radars, and many other instruments. All this data is, of course, publicly available. You want to play with the data, you want to plot the data, it's possible. And there is also the possibility for campaigns. There are also instruments that are sporadically installed in Antarctica. And with some of the upcoming NASA missions for the aeronomy community, I know that there are more than 100 instruments that are planning to be deployed on the ground to observe the aurora. So those should be available for PUNCH too. So hopefully I have convinced you today that we are looking forward to work together. I think the high altitude aurora is very mysterious, and we do need every instrument that we can put our hands to put this into context. So hopefully we can create that coordination between the in situ and ground-based observations that we need. And there is also, remember that there is also the possibility of using that non-traditional data that sometimes citizen scientists can provide. So go Punch.
Thank you so much, Bea. Okay, our next speaker is Russ Howard. Come on up, Russ.
Great. Thank you. So thanks for everybody for staying this late. I'm going to talk about something completely different. What kind of observations could Punch make to help with understanding the zodiacal dust? Dust is in orbit about the sun. There's a family of dust objects that are called the Jupiter family comets, which are in orbit about Jupiter, but then others are very long period comets. I mean dust particles. So these dust particles reflect scatter light from the photosphere, and it's called the F corona because the light shows the Fraunhofer lines that are in the photosphere, whereas the K corona, the scattering due to electrons, don't show that they blur out the spectrum, and so it's just those individual spectral lines are not seen. There have been a few major contributions defining the visible light's properties of the F corona or zodiacal light. And the F corona really refers to the light that is close to the sun, whereas the zodiacal light was the region that was seen from Earth. And so it was, but they're used interchangeably. But the dust cloud is called the zodiacal cloud. So I'm using this hyphenated term or combination term F corona zodiacal light. So the Helios mission consisted of two spacecraft launched in '74 and it lasted till the early '80s. And Christoph Leinert and Eberhard Grun really published a whole series of papers that really defined the zodiacal light from 1 AU down to 0.1 AU. It was really amazing, and we'll talk a little bit about that. The Skylab mission, 73 to 4, there was a paper that defined the F corona as seen out to about 6 solar radii by Saito, Poland, Monroe, which I referred to in my paper about the F corona, or not paper, but software that described if you called IDL and wanted to know what the F was, here it is. And then Kimura and Mon wrote a paper where they summarized a lot of individual observations of the zodiacal light from balloons and whatever in the late '80s. Then, in preparation for the Parker Solar Probe, Guillermo Stenberg and I engaged in a series of analyses to try to define exactly what the observations were seen from 1 AU, so that when we're on this Parker Solar Probe, which is going into regions that we haven't seen before, haven't gone to before, that we would be able to say, well, this is different. So, but prior to that, we thought that the F corona or the zodiacal light was absolutely constant. There really wasn't any interest in it. And so our objective was to get rid of it, to find a background model, get rid of it, and then go on to the look at the electron density structures. But in fact, that's not the case. It is really amazing, and I hope to incite you or excite you in some areas. So this is from stereo. This is using the heliospheric imager, that one of the high one on stereo. We did a calibration roll, and so you could see the entire 2D corona. And you notice that it's elliptical, and that there is an axis of symmetry. And that axis of symmetry is actually on the orbit of Venus, which is what, in fact, Parker Solar Probe is. So we do not see any fluctuations in any motion in the intensity. It's really amazing. It's really great. So, but what we tended to do was to emphasize the properties of that, and that's what Leiner did. He defined the radial gradient, for example, as a function of that central axis, and then defined an offset from that central axis to get the rest of the corona. This is made up. This calibration roll, by the way, which is what I mentioned a day or so ago, was made up. It took about 8 hours for this to happen, and the images are slightly off. They're not, the images don't match exactly from one to the next one, and so there's a slight gap in between them, and that's the problem that we're going to have. So there are 4 ways that punch can contribute, I believe. One is in the brightness distribution, the brightness asymmetry, the polarization properties, and then various oddities, which we'll get into. The asymmetry was, well, I'll get into that in a bit. So brightness distribution. So here's what we measured in terms of the function of time for 6 years of this, until from launch until the Cytherea spacecraft went behind the sun. This is what we saw. This fluctuation in 3 different, these are 3 different positions, angular positions from in the sky. And what you see is this yearly variation in the brightness distribution. The 0 would be the line of where the line, the 2 axes, the axis of symmetry of the dust plane crosses the ecliptic, and then there's a maximum and a minimum of a few degrees. If you plot that, instead of in time, if you plot it in terms of ecliptic longitude, you get, in fact, this very, very nice, these are now weekly averages, I think, or medians maybe, of the intensity values for 6 years, and it's all on these lines. It really is constant. What you do see are issues related to planets or the Milky Way, but it really is it's amazing. But it does vary in the ecliptic. You'll see this daily variation. So we plotted then the gradient, the brightness gradient, and as a function of, again, of longitude, and you can see that there is this peak of around 2.3, e to the minus r to the minus 2.3 is that. The black line is the slope, and the red line is the standard deviation of the fit, and it's really fairly good. The plot below it is we considered 3 different positions of the sun, in radial distance from the sun, and as you get closer to the sun, the gradient increases. And finally, at the bottom, the red one on the bottom is in fact almost circular. You can see that the peak at the nodes is almost gone. And that's because it's becoming more and more circular. So what can PUNCH do? First of all, they can verify that this is they agree with this this brightness gradient. But then, can you see variations in the orbits of there's dust in the orbits of Venus and Mercury and Earth, and can you see that dust? It's just a few percent, but if you have these very good statistics, you should be able to see something. In fact, we found Mercury's orbit to be very difficult, but we definitely feel it was there. Can you see slight enhancements anywhere? Possible asteroids or dust sublimations, which we'll talk about in a bit. And what is the brightness distribution as a function of latitude? As I said, we did not look into that. Leinert's, we've always used Leinert's values, and so on. So you can look at this later. Also, oh, 5 minutes. Also, there is a possibility of seeing interstellar dust. In alternate solar cycles, the heliospheric cloud is going into the interstellar dust and causes a brightness distribution, and that is becoming quite interesting. People are seeing that dust because of the makeup is different slightly than our dust, and so it's apparently there. And so, can you see it? But that only occurs every other cycle, and I'm not sure. These are this is the longitude. It's centered at about 259 degrees ecliptic, but I don't know which cycle it is. So let's turn to asymmetry. This is this was a question that had been running around for a while. And so this is a plot of the center of mass of the solar system. The sun is a yellow dotted line. It's difficult to see. Oh, I can't. Oh, here it is. Here is the edge of it, and you can see it going around this way, up there. Right in the measurements that we were taking from Parker, we were looking at observations in this for 2021 to 23. The center of mass of the solar system is a whole radius off the limb of the sun. That's huge. So what happened? So this is a diagram that shows a little bit what that is. These are lines pointing to, the red lines are pointing to Saturn. The blue dashed lines are pointing toward Jupiter. The SSB is on this track here, and these are the points at the beginning at each of the perihelia of the encounters, the 6 encounters. This represents the asymmetry of the ratio of the brightness, average brightness of each latitudinal or each radial bin as a function of elongation of the what's it called? The perihelion. And in the inward bound, it was approximately 2 to 4% higher than the median. On the outward bound, it was also the same distance, except after in the third orbit and beyond, it starts decreasing. What in the world's going on? So first of all, that asymmetry of north to south, we definitely proved that it is due to there is a gravitational effect. That symmetry we then plotted as a function of the separation of Jupiter to the SSB, and there is a reasonable correlation. So in this next plot, I shouldn't have put it here, but I did. What you see here is these various colored lines are the the total brightness of 4 different encounters. And it's showing that in fact that the relative to the 0 line is in fact our background F coronal model. And that is what it's saying is that the K corona is becoming a little over 10% of the total brightness in compared to the F. Normally, it's a factor of 100 dimmer than the K is 100 dimmer. And one of the orbits, in fact, a CME pulled out dust, went below that level, that background level, and pulled out dust. So polarization quickly. There's hardly any measurements of polarization. So as I mentioned earlier this morning, that Rhino in fact had the measurement of zodiacal light that as much as 20%. So I think that is something that PUNCH will actually have free range in, be able to do a lot of stuff on it. Anything they do will be an improvement. So brightness oddities. Oh, one was the first is the interstellar component. I'll talk a little bit about that. We've seen these Mercury enhancements. We're particularly interested if you can improve on the Mercury in orbit. Dust sublimation is a big deal. So people have been looking for it. It had been predicted that there was a dust-free region around the sun, predicted in 1929, that people have been searching for using IR and visible measurements. We never saw it. We couldn't see it. It would have been predicted to be at about 6 solar radii, 5 to 6 solar radii. When we saw a dust depletion region starting at around what we thought was 19 on the very first pass. We then looked using the telescopes that had more of a tangent to that zone, and what we found was this: that in fact there's a dust increase that is an intensity increase starting at around 35 solar radii, peaking at 4% above or 4 or 5% above the background at 25, and then there's this very sharp drop from then on until the limit of our measurements at that point, which were 10 solar radii. And you can sort of see a little bit of an upward peak, and that's due to the K. So the point is that this zone completely surrounds the sun. You can see there's no break in it as Parker goes through this 270-degree track around the sun. It's just amazing. So the question is are there any other zones outside of this? There's no zone inside here, we believe. This looks all quite nominal. Are there any? PUNCH might be able to see zones beyond it that we have not been able to see. This is not visible from Earth, because you can imagine if you're looking down from the right to the left, what you'll accumulate is all of this. You'll accumulate this integration along the line of sight of all these different points, but then the drop off following it hides that value, hides that peak. You do not see the peak. It's impossible to see from Earth or from 1AU. So that's it. Here's my total summary. Thank you.
We're going to do questions at the end. Yeah.
Go PUNCH.
Go PUNCH. All right, continuing on our theme of rib bone science, things that PUNCH is going to tell us about, that, the serendipitous perhaps. Yeah, we're going to go to Wei Liu, who's going to be talking to us about sun grazing comments. Get this fixed.
All right, thanks for sticking around. switching gears again, comets. So comets are probably the second most fascinating heavenly bodies in the sky that grabbed attention of our childhood eyes, including myself. So we are interested in those so-called sun-grazing comets, which are those with very close perihelion distance, within about 3.5 solar radii from the sun's center. Those are very interesting objects because there are twofolds. One is for their particular interest or position in terms of the physics for comet science, because the close encounter with the sun can expose their otherwise inaccessible interior, which can provide clues to their composition and structure. So because comets are basically the remnants of our early solar system, that can provide a lot of clues for solar system formation and also life origin and all of those. The second interest for us, solar physicists, is comets are really like free solar probes. When they go very close to the sun, into the low corona, for example, I'll show you a few examples. So that can provide some conditions. We can use them to probe the condition on the sun, for example, magnetic field and density structures of the corona. So with that, I do want to disclose LASCO on SOHO has actually seen comets in the chronograph for like over 5,000 of them for the past 30 years. So there are a lot of comets. However, those made close to the sun, they're pretty rare. We only got 2 comets so far captured within UV imagers very close to the sun back in 2011. Both happened within half a year. And then after that, we thought, well, there were more comets coming, but for over almost 1.5 decades, we have not seen another one until maybe last year. I will show some examples. So with that, our understanding of sun-grazing comets would not be the same without the contribution and the groundbreaking discoveries led by 2 of our colleagues, Kara Shriver, John Brown, who are known for great science in other areas of solar and heliophysics, but both of them had been very passionate about comets, and myself included. That's why I'm here. So this was a discovery made back in 2011 by Carroll himself after looking through the data with the AIA. Because before that, we had no idea if we can capture a comet in the solar corona that's so close. And he knew, well, there's comet coming. I think we got some alerts. He sort of knew where to look, but still very difficult. So as you can see from this chronograph, the comet flying through the chronograph and then disappear up behind the Carter disk. Then it's a game to find where it is. That's very challenging. And here's an example from AIA. So it's very, very tiny shining spots. So this is actually processed image with contrast enhancement for that area, but otherwise it's very difficult to find. And there's a close-up of that region. As you see, the background sun corona is very bright. There are a lot of structures. It's really difficult to capture that comet. Here's a great movie made by Barbara Thompson. So which is the movie for the Lovejoy back in 2011 and in AIA 171 channel. The top panel shows basically every single frame is background subtracted. The bottom panel shows the so-called persistent movie. Basically, you're adding every single frame on top of existing frames. So that can show the lasting feature of this comet. Those actually the tail deposition of the comet material into the corona. What you see here, an interesting feature is the tail material basically bifurcates along the trajectory, some moving toward the south, some moving toward the north, which has some interesting implication we can see from the next slide. This is a great study made by Cooper Downs in the audience. So the left shows a few snapshots of the comet Lovejoy tail behavior, as we saw from the previous movie. And the right-hand side shows the mass model reproduction of the coronal magnetic field and the UV emission reproduction. So the key thing here is the comet material. I think about it. They're neutral material. They're basically comet. A comet is a dirty snowball. It's a rocky, icy body. Those are neutral material. But once we get into the low corona, into the near sun environment, the intense solar radiation is going to supplement the material, and they get quickly go through photon dissociation from molecules, atoms, and then go through ionization by basically mostly by charge exchange and also collision, and a bit by photon ionization. So they get into ionized. But think about what would happen once those particles being ionized. In the presence of magnetic field, we know particles got stuck onto field lines. So there's basically a phase transition from neutrals to ionized material happening very quickly. Before that, they're going to fly through the corona magnetic field, don't care about it because you are neutral. But once they get ionized, they get stuck onto field lines. So they can move along field lines, but not across it, mostly. But there's exceptions, I'll show later. So depending on where you land onto the field lines, if you are also depending on the trajectory of the comet, if you are landing on field lines going that way, it's going to stream in that direction. If your field lines going this way, when the particles get ionized, they're kind of streaming this way. So that's why you see there some tail materials being bifurcating from the trajectory, as what Cooper showed in this modeling. So one exception to what I just said is there's also motion not only along field lines, but also perpendicular to it. So those are the so-called J maps along the trajectory of the comet, as we see on the right-hand side, basically a narrow slit along in the image. You stack them together to make this so-called J map. This very steep slope and at very constant speed, that's basically the nucleus velocity on the order of the escape velocity on the sun, which is about 618 kilometers per second on the surface of the sun, but higher in the corona is roughly about 600 kilometers per second. And on top of that, you see those like feather-like material, basically what you saw from the movie. There's a material deposit onto from the tail of the comet onto the field lines. You see some gradual deceleration of those tail material, and some of those even turn it backward. So we found those are evidence of you're loading your magnetic field with comet material, which comes at very high momentum. Think about the 600 kilometers per second. So basically, you're loading the magnetic field with some momentum, and the field is going to bounce back with recoil. Basically, like what we see from eruptions. There's recoil happening from magnetic field lines, and this is basically opening a door for new diagnostics, like we call comet seismology, like coronal seismology. We heard a lot from those perturbations by the comets. And so more recently, last year, we got a new comet back in October. There's another one potentially can make to the very close to the corona, and we made the very big team to do this coordination. And this is the orbit projection onto different assets, PSP, orbiter, Earth, and other locations. And so we energized the community to do some very interesting campaign with a very short notice. So this is one example we did with an SDO. We off-point the SDO spacecraft for roughly about half solar radii of this nominal pointing, and then on the right-hand side is the movie showing that the result of that, basically. So we did this up point, but however, we didn't say anything because the comet was so faint. But here's the catch. Solar orbiter and METIS actually captured the comet. If you can see in the lower right, there are very faint feature coming off in here, and there's some preliminary sign of breaking up of this comet. This is Lima alpha in UV, So that's some interesting science we can do with this. This is very preliminary. Matthew's team was very excited about this. I think, to my mind, I think it's probably the first discovery of breaking up in UV at this wavelength. Looking forward to PUNCH, but before we get there, my second last slide is what you can do from if you go further out from the inner corona, as I showed in my previous slides, basically focus on the UV corona. If you go to the chronograph, this is an example what Craig DeFrost himself did 10 years ago with stereo. So basically, they found those wiggling motions from the tail material from the comet, and found evidence of some eddy or turbulence in the solar wind. So these sort of things can be done with PUNCH with much higher sensitivity, spatial coverage, spatial resolution, all of those. So that leads to what we can do with PUNCH. And I think one important thing is that PUNCH's field of view coverage can really provide a seamless coverage from 180 solar radii to 6 solar radii, and then from there on, the in smaller field of view assets like AIA or stereo UI can take over for UV coverage. So we can provide a full coverage of the evolution of Sun-Gores comets, and also with brightness or total polarized brightness measurement, we can get some idea about the density, things like that. So that's really exciting. We really look forward to it. Go PUNCH. Thank you.
Great, thank you. And for the final talk of this session, we're going to have a talk from Yoon-Soo Sung, who's going to be talking about another ribbon science topic, potential polarimetric signals in solar system objects. This, however, is going to be Yoon-Soo was not able at the last minute, was not able to come, and so he gave us a recording, and he will be available for questions during the Q&A panel of everybody in this session. So let me go ahead and cue this up.
I'm sorry I couldn't make it there because of my private reasons. The presentation is about solar system objects polarimetric science cases using PUNCH mission data. To introduce the polarimetry in solar system small body sciences, one important concept is polarimetric phase curve, or PPC. This PPC is basically a function of polarization degree as function of phase angle alpha, where phase angle alpha is 180 degrees minus scattering angle theta. So this alpha is basically sun, target, and observer angle. When the unpolarized sunlight is illuminating the ALS body and it is scattered on the surface, then the scattered light will be polarized. And this polarization can be described by the intensity is perpendicular and parallel with respect to the scattering plane. For Fresnel or Rayleigh reflections, this perpendicular intensity will be higher than that of the parallel intensity. So it will be natural to define the polarization degree as perpendicular minus parallel divided by the sum of them, which is minus Q over I in Stokes parameter language. If we plot this P value as function of phase angle alpha, then virtually for basically every single experiment laboratory samples and also celestial objects, we always see this characteristic curve. It becomes negative first, and it changes its sign around inversion angle 10 to 30 degrees, and then it peaks at around 100 degrees or something like that. The maximum polarization degree is described as P maximum. Because although other parameters are very important, they have certain important and interesting correlations with physical parameters. But in this presentation, because of the time, I will just give you an idea of why this P maximum is interesting and important. But before that, why PUNCH is interesting for this kind of observation. most of the asteroids are concentrated between the Mars and Jupiter orbit. These are called main belt asteroids. Purely geometrically speaking, because of their orbit, it's very difficult to observe them at phase angle alpha higher than 30 degrees. So in this PPC, we can obtain the PPC only up to somewhere here. Above around P maximum, it's basically impossible. For the asteroids that comes close to the sun, then we can obtain that high phase angle data. But the problem is they are close to the sun. So the two very important limiting factor is that first, we have to have a observatory that allows us to point very near the sun. And secondly, that observatory has to have a polarimeter. And why do we study P maximum? Sorry. Because it is one of few ways to discuss grain sizes of the scattering surface. Grain sizes we discuss are generally ranging from micrometers to millimeter or centimeter scales. They are too small such that even in situ mission data, we cannot really distinguish whether this is centimeter or micrometer scale particles. One such approach is so-called thermal modeling. This is for the theoretical modeling that uses grain size as a free parameter to fit the model flux to the mid-IR thermal radiation flux. As any theories does, it also assumes a lot of simplifying assumptions or approximations. And on top of that, there are a few magic numbers that were calibrated using Apollo lunar sample data. So we are not completely sure if they can be applicable generally to other asteroids, for instance. So that is the limitation of this theoretical approach. The two other approaches are empirical polarimetric approaches. First is high phase angle P maximum interpretation, which I will explain shortly. And the second is the near infrared multi-wavelength polarimetry at low phase angle, which I have recently been working on. On the right-hand side, this shows a two-dimensional parameter space made by the maximum polarization degree and the albedo of the laboratory measurement samples. The different samples, these samples include Luna fine Apollo or Luna mission samples, and the terrestrial rock powders, meteoritic samples, etc. These green lines guide our eyes to follow the same grain size samples suggested in 1980s and 1970s by the experimentalists. It is interesting that regardless of the origin of the samples, they have very strong, tight relationship or empirical trend that the grain size increases as the polarization degree increases for a given albedo. This we do not have a clear unanimous agreement on the physical or theoretical understanding of this phenomenon, but at least empirically speaking, this is quite tight relationship, and we use that to estimate the grain sizes of the surface from remote polarimetric observations. Now I want to introduce you an interesting case, asteroid 3200 Phaeton. It is the Gemini's meteor shower parent body, and it is just as Destiny Plus mission target, which will fly by in 2030. It is one of the largest and thus the brightest near-Earth objects, so it is very widely studied asteroid. I also participated and led the paper that theoretically explores the reasons why it can eject dust particles that can eventually become the Gemini's meteor stream, and our team has investigated the dynamical simulations or evolution trajectory to understand when the dust particles should have been ejected to explain the current Gemini's meteor stream. In the polarization viewpoint, this object is also a very interesting object. In 2016, we conducted an observation campaign to obtain the polarization of asteroid Phaeton at very high phase angle, and we obtained 50%. These data were published in Nature Communications. In 2017, an independent group, they reported that the polarization degree was around 40%. We after realized that in 2016 we were observing North Pole, and in 2017 Southern Hemisphere were visible. So as I briefly mentioned before, large polarization degree can be interpreted as larger grain sizes. So it can be qualitatively interpreted that in 2016, when we were looking at Northern Pole, the Northern Hemisphere, it is consistent of large particles, while Southern Hemisphere, it may contain smaller particles. Interestingly, from a theoretical modeling viewpoint, Thermal Modeling Society, Eric McLennan published a paper recently and independently from polarization studies, a coarse-grained northern hemisphere and fine-grained southern hemisphere 2-grain size model is necessary to explain the multi-epoch thermal data, including WISE and Spitzer data. So these are quite consistent with each other now. And also considering that this is the only case that shows this kind of very strong polarization dichotomy, any new data points at very high phase angle will be very interesting. And if we want to know if this distribution can be kind of continuous depending on the sub-Earth latitude value. In summary, high phase angle polarimetry is a scientifically interesting topic to study, but not many data points are available because of the unfavorable viewing geometry, and PUNCH is a perfect observatory for such kind of observations. And small phase angle data set will also be obtained from PUNCH mission, I expect, and that will make the PPC database very dense and much more diverse. And I'm expecting that a lot of statistical analysis and taxonomic type classifications, etc., will become possible. Also, because of the time limit, I was not able to talk about comets, but comets will become very bright. The only limitation that we have from ground-based observatories are weather and the telescope time. But because in space, we will PUNCH will basically monitor the near sun region, and I'm expecting that a wide phase angle coverage and time series PPC of comets will be available, which I am very excited about. So on top of the PUNCH mission, small additional effort will lead us to a great input to the small body science societies. So I am very much looking forward to this PUNCH mission, and thank you for attention.
All right, thank you so much, Vinsu. And what I'd like to have now the speakers from this session to come up to the podium. And so I'm going to go ahead and invite you to unmute so you can